So we did,
yes, it's a very good idea. Probably stop it. Shall I lift it? I put it.
good morning. I'm going to present Valiant's result. I'm not Valiant. Where he defined, so the biggest question we are trying to solve is the P versus. I can try. The biggest question we are trying to solve is the P versus NP problem. And Valiant in '79 defined an algebraic version of this problem, which we today called the VP versus VNP problem. And V stands for Valiant, as far as I know. So when he defined these two classes, VP and VNP, he also gave a complete problem for VNP, and this problem is the permanent. And I will start by defining these two notions formally. And then we'll start discuss the proof of this statement, the completeness of the permanent. But before defining these notions, I want to define the model of computation we will be working in. So in this model, we are interested in computing polynomials. So we will have some field, f. In some point, we will need to assume that f is not of characteristic 2, but otherwise, f can be an arbitrary field. You can choose whatever field you want to think about. And we will have some set, usually of n variables. And our purpose in this computational world is to compute some polynomial in the ring. So we want to compute polynomials in this world, and the operations we are allowed to do are the arithmetic operations. So we are allowed to use either plus or times, and the computation will be done by an arithmetic circuit, which is a very simple object. We write the input variables in the bottom, and we can write some field elements. And then we are allowed to take sums of things that are previously computed and product of things that are previously computed. And things like that. And every position in this directed acyclic graph computes a polynomial in the obvious way. If we computed, this computes x1, this computes x2, this computes x1 plus x2, and so on. So this will be an arithmetic circuit.
So all elements of the field.
So yeah, you are allowed to write here whatever element you want. Yes.
And do you need to be able to compute in the field?
We don't assume this in this. It's a formal. We assume that we can compute. So when we write, like, this means that this computes alpha times beta, whatever this is. Okay?
But division isn't that.
So it can be shown that division is not helpful in computing polynomials. This was proven by Strassen at some point. Okay.
Use a factor of n in the size, but
Yeah.
for polynomial size it doesn't work.
Yes. Okay. So we will usually denote an arithmetic circuit by phi.
Isn't the non-product is of 2 elements?
Yeah, we always take 2, although it does not really matter because we assume, so the size, so this will be an arithmetic circuit, the size will be the number of edges. So it does not really matter. And every position in this graph, we'll call it usually V. We'll call it a gate in the circuit. And we will have this circuit will be the sub-circuit that is rooted at this gate, everything below it. And we will denote by phi hat of V the polynomial that this circuit computes. Okay, so this is a circuit, and this will be a polynomial. I will remind it whenever we'll use it, I hope. What else? Yeah. Another object that we'll be interested in is an arithmetic formula. A formula is a circuit where this graph is a directed tree. So every gate will have out degree 1 in a formula. So a formula the computation graph will be a tree. And for example, this is not a formula because the out degree of this gate is 2. We use it twice. So
Use the variables twice. You use the leaves twice. The variables you can use twice.
no, we
No, he's right. There may be several edges coming out of a single variable.
no, it does. We duplicate it.
Yeah, you do. It's the same thing. It's the same thing. Duplicating it or
Yes, but we duplicate it. So
He likes the graph to be a tree.
yeah, I want the graph to look like this.
No, I understand, but you could say we duplicate vertices. We don't duplicate. I mean gates. You're allowed to duplicate only leaves, only variables.
Yeah, so yeah.
So every node has either a variable, a constant, or an operation.
Yeah, so yeah.
And it's a tree.
Yeah, we have a tree, some tree. In the all the leaves are labeled by variables or field elements.
But even a variable can be used once.
No, this is
Can be-
yeah. For example,
It's like a normal formula in mathematics.
um,
Just don't need the parentheses.
yeah, and every gate here is labeled by something. Okay. So this is the object we want to compute, polynomials, and the model we are allowed to compute it are either circuits or formulas. And we are interested in computational questions like, given a polynomial, does there exist a polynomial in n variable? Does there exist a circuit of polynomial size that computes it or not, and these type of questions. So now we'll define the algebraic analog of P, which is VP. So a family of polynomials will be in VP if there exists some polynomial P such that three things hold. One, the degree of Fn is at most Pn. Two, so a polynomial will be in VP, will be in what we think of easy polynomials if its degree is polynomial and it has a polynomial size circuit that computes it.
So Fn are polynomials in n variables.
Yes. So we have this conditioned.
Yeah, it's just not clear that Fn are polynomials in n variables. Yeah.
Yes.
So what is given?
We're just trying to define a sequence, an infinite sequence. Not a particular polynomial, so not a 3 by 3 permanent term. Or permanent. So this is a sequence, F sub n, a sequence of polynomials that are somehow similar to each other, like all determinants and so on. And that's a condition when it's easy. It's easy if it has a circuit that's small, and if its degree is also small. These are the easy polynomials.
Yeah, maybe one example of a polynomial in VP is the determinant. The determinant is a polynomial in n squared variables. Its degree is at most n, and there is a circuit to the power of 3, I think, that computes it. So I don't want to explain the circuit, but it's you use Gaussian elimination. Yes.
This is about VP, so
You can remove it.
Yeah, this is if you, yeah, you can think about this using division, and then you can move the division out somehow.
But there is also an explicit,
Yes.
pretty natural sequence.
but one has also to decide sometimes if two things are
You
equal.
don't. You don't. No. You never have to decide with zeros. You can write it just with plus times.
And another family we want to define is VNP.
I mean, but actually, maybe since you mentioned determinant, maybe it's worthwhile saying that there is also a formula for it of side n to the log n.
Yes.
And it's a really nice open question. It's maybe not trivial, and we don't know what it is.
So, yeah. What Avi said is that formula size n to the power of log n, and this, if we are dwelling on this, this turns out to be, in some sense, always the case. So first, it seems like a very, so first this algorithm this circuit formula was discovered. And then actually they noted that every circuit of size S, so for every family of polynomials in VP, the formula of Fn. So this is not a very difficult theorem to prove, but I don't want to prove it now.
No, it's not a corollary. It's first the result about determinant was proved, and then it was generalized to this general theorem, which implies the result about determinant.
It's not really some kind of notion of completeness for the determinant that implies that it's a corollary or something?
No, it's not completeness for determinant. Because it's a result about circuits. The determinant is complete for formulas.
This leads to another discussion about the completeness of the determinant, but let's not discuss it now. And what will be VNP? So we want to define a family of polynomials in VNP. So it will be defined as follows. There exists some g of n, some family of other polynomials, and some p of n polynomial
No, it's a family again. You'll see that. Maybe you want to write Fn of, yeah.
Your pen is in VP?
So now we want to define a bigger class than NP, than P, that will capture somehow the definition of NP. So we will say that a family of polynomials is in VNP if there exists another family of polynomial that has a polynomial size circuit, and Fn can be written as a Boolean sum. So each one of these polynomial in many bits is a bit, where we sum g over all of these Boolean values. One way to view this, how is it related to NP? So in NP, we have a statement of the form there exists an E such that g of x and E is 1. This is a sort of statement we have in the definition of NP. And here, instead of an existential quantifier, we take a sum over the field.
Why is the sum only over the Boolean values? Is there,
The field may be large. You can't take a sum over the whole field, so that's natural.
I wanted to make
It's good for everything. This is good independent of the field.
But I guess for polynomial, for large fields, it's different, and then this makes more sense.
if you take a Boolean circuit and just arithmetize it in the obvious way, this existence is really a disjunction, a big disjunction of vectors, Boolean vectors of length P of n. So when you make this disjunction arithmetic, you just write the sum. That's natural. It turns out to be, useful, leads to, nice theory. So it's a good choice.
Okay. But I guess for polynomial size field, if you only care about polynomial size, then it doesn't matter. So.
There is one difference between. So what you said is maybe you want to encode the field by bits. And arithmetic operations don't allow bit access to the field elements. So it may be a different theory. So, okay, this is the definition.
I'm still confused about the index because you have fn and g index Pn plus n.
Yeah.
There's more variables.
So.
But that's the number of variables.
Yeah.
But it's
Yeah.
Gn, which was previously mentioned.
Yeah.
Well, it's just a family
It's
of the whole n.
yeah. This is a
But
sequence.
It's a polynomial in no variable.
Yeah, every Gn is a polynomial in n variables. Every Gn. So these are sequences of polynomials. This bracket Fn and Gn are families of infinite families of polynomials. And when you define Fn, you are using the member of the family G, which has more variables. Polynomial in many variables over which you project.
And the last line is a motivation or it's part of the definition?
No, it's just a motivation. Like.
It's just in NP you also take more variables that you get for your guess of which one of these is this junction. So you will take this one. You'll show an example of
Yeah.
what
Maybe the tip. Yes.
So just for an infinite field, did anybody look at defining this using an integral over the other variables?
What
Over
this.
the real numbers, you could do this. Let's say integrate over some other variables.
So this is a definition that holds over any field. There is, you can maybe define some theory with arbitrary integration where you define the measure somehow, but let's not do this now. So maybe the simplest way to think about it, and we'll try to explain it later, is so maybe the simplest way to think of a polynomials in the class VNP is if we are given a monomial, we can decide the coefficient of this monomial in the polynomial Fn in time polynomial in n. So one example of a polynomial in VNP is the permanent. So and why is this so? Because given x1, 1, x1, 2, x, n. Given some monomial in the variables of the matrix, then the coefficient of this monomial is either 0 or 1, and it is 1 So the coefficient is 1 if and only if the matrix E11, E12, E1n, ENN is a permutation matrix. And deciding whether a given list of 0 and 1 defines a permutation matrix is a simple task. We can do that in polynomial time. So, does it make sense? Okay.
Exactly what can find the coefficient using what?
So using a Turing machine, for example, or a Boolean circuit.
That will imply automatically that it's VNP?
Yes. So I will try to explain why this statement is true later on. But this is not a formal statement, just a way to think about it. So the polynomials in VNP are explicit in the sense that if we know a monomial, we know its coefficient. Okay?
It's not an if and only if, but you're saying it's a good. I mean, but the if direction is formal.
Yes, you can make it a formal statement. Okay. And now we want to define complete problems. So what will be a VNP-complete problem? It will be a family of polynomials such that 1 it isn't VNP. So a VNP-complete problem will be a problem that is in VNP, and every other problem in VNP can be embedded into F, where this embedding is a simple substitution. So let's say that G is in variables y1 to yn.
Can be one small variable.
Yeah, so G of P of n. Then f of n is G of P of n. When we write y1 is x1, y2 is 0, y3 is x1, and so on. So fn, so I confused the so fn is a polynomial in many variables, which let's call them y1 to ypn. Now g is a polynomial in x's. So how do we get from a polynomial in many variables to a polynomial in n variables? Instead of y1, we just write x1. Instead of y2, we write 0. We can substitute every yi by either a variable xj or a field element. So these are the two things we are allowed to do. So this is what we call a VNP-complete problem. And the theorem that Valiant proved is that the permanent is VNP-complete. Okay, and this is what we will try to explain. to prove this statement, we will prove three things. So there are three steps. The first step is to simulate circuits by Boolean sum over formulas.
Boolean sum is exactly what appears in the definition of VNP.
Yes.
That's what you call Boolean.
So formally, what does this mean? So we want to take Fn. So okay, let's keep that. And this will have a circuit of size Sn. And we want to write it as a sum over Pn. The same, exactly the same thing, but this will have a polynomial Sn size formula. So we want to take any circuit and write it as a Boolean sum over an arithmetic formula. Okay, this will be the first step. I think it will be clear eventually why we do this.
You mean if a sequence is in VNP, then all the you can change this GN in the definition by formulas.
Yes. So yeah, so this will imply that exactly what you said, that this is the way it's denoted usually, that VNP is equal to VNP subscript E, where this means that the polynomial G is computed by a formula. Okay, and so in other words, in the first step, we will show that we can assume without loss of generality that this thing has a small formula instead of a small circuit. So this will be the first step. Yes.
I mean, given that you allowed to add auxiliary variables, and then you make it a formula instead of circuit.
It's a little more complicated.
The second statement is a universality of the permanent and actually also of the determinant. And what does this mean? This means that we can take a formula of size S. Let's say there is a polynomial computed by a formula of size S. There exists a matrix M of F, which is of roughly size S by S, so that F is the permanent of MF.
This is embedded. Yeah, it's embedded in the same way
Yeah.
as projection.
So yeah, MF will be a matrix that will contain every entry here will be either xi or f.
General element? You need all of them?
Yeah,
All the elements that appear in the formula.
in the, yes. And I wrote here the determinant because exactly the same thing holds for the determinant. There exists a matrix M prime of f such that the determinant f is equal to the determinant of M prime of f. So this is called the fact that we can simulate formulas, but polynomial size formulas by polynomial size determinants or permanents is called the universality of these two functions.
It's another completeness result
Yes.
for
Completeness result, because it isn't in the class.
So
yeah, it's hardness.
using the thing that was written here, or here, this implies that the determinant is complete for the class QP, and this is quasi-polynomial size formulas or circuits, it doesn't matter. So, but this is just a comment. Never mind. So this is the second step of the proof. And the third step will be to use the properties of the permanent, and it's a statement that should not be true for the determinant as far as we know. This is like what should make the distinction. So the third statement is that permanent allows Boolean sums. And what does this mean? This means that if we have a matrix M, so let's say it's S by S, and there is some element B that appears in M, SB times, so
Element means variable.
yeah, some entry in M that appear so for example, like x1, 0, x2, x1, 0, 1, x1, 0, 0. Then B could be x1, and then S of B will be 3. x1 appears 3 times. Then there exists a matrix M prime of size S plus, let's say, 7 SB, S plus 7 SB, of roughly the same size. So M prime will be of roughly the same size, but the permanent of M prime is the permanent of M where B is 0 plus the permanent of M where B is 1. And so we want to take a Boolean sum over the permanent of M, and this is like in the definition of VNP. We want to substitute a variable by either 0 or 1, and we can do it by permanent of roughly the same size. So this is the third statement.
The SB was what it's like the maximal number of appearances of
So there is a specific variable b,
Oh, right. These
And-
pieces.
I'm confused. So, in the matrix M, what kind of entries do you have? Only variables?
Variables and constants, yeah.
yes, yes. Mhm.
And you fix one of those variables which you call B.
Yes, we choose one of these variables. And
And for every m, right?
yes, for
What-
every.
For every m, there is one.
Yes.
And for every variable that you take as b.
Yes.
Yeah.
Okay, so how does these three things imply the completeness of the permanent? So let's take some f in, so I will lose the sub n. We'll think of a polynomial as a family of polynomials. So let's assume that f is in VNP. This implies that f is a sum so we take a polynomial in a VNP, we write it as a Boolean sum over a formula due to the first step. Now, this has a polynomial size formula, so this is equal to sum over E. The permanent of M of G. So this is due to the second step. This has a polynomial size formula. So this is a polynomial size matrix. And now we do this Boolean sum one by one. So we can write it as a permanent of M prime of G, where the size of this will be at most S plus 7 S squared times S plus 7 S squared. Well, to do this, so we want to sum over E1, then we use the third step with E1. Then we get a sum of two things with one permanent. And we now make the matrix even bigger. So this 7S squared is 7 times S of E1 plus S of E2 plus S of E something.
Wait, is that clear? Because it gets composed. So first you do E1.
Yeah. Yes. So this is this works. You just
Oh, yeah, sure.
okay. I just
Square it.
A square is just
so an upper bound on this is S squared, because they form a partition of the at most a partition of the entries of the matrix.
Exactly, actually, a partition, unless well, the
No,
constant.
no.
Some of them are the original.
Yeah, you leave the x's you leave alive.
Ah, right.
So you
I don't understand. The first step, S got bigger.
yeah. So
It has to be and it is in factor.
So this has a formula of size P of n, this thing. This means that this matrix is P of n by P of n.
No, he's asking after the first step, S increased, so S got bigger.
So
Yeah, but it's just
Ah,
additive. You
yeah,
see the
yeah,
sign,
this
the
is-
formula,
yeah.
Put parentheses first of all, so that signs will not confuse.
maybe,
No, you don't really need.
maybe just take off the side length.
Yeah, it just says the size.
Ah, okay.
It's just S plus the a multiple of the number of occurrences. of
Yes.
this variable.
Yeah.
That's all.
Yeah. This is a
There's no
very good
constant,
point.
right?
Yeah.
A picky point, but the SB could change once you go from M.
Yes. It doesn't. So we,
So it doesn't.
yes,
It doesn't have that.
yes, you're right. Yeah, so this step I think will be fairly clear how this works. It's not a very complicated. Okay, it's debatable. Yeah, one thing about so you can. We will see later that if you don't want this to be additive, but you just allowed, say, 2s by 2s, then this will work for the determinant as well, or something of this form. But this, after you do polynomially many steps, will be exponential. So, yeah, this plus is very important, and it only works for the permanent.
And it does not work when the characteristic is 2.
Yes, you're right.
So starting when did you achieve characteristic value?
Just the
So
third
yeah,
step.
only this.
This we know that it doesn't work for like determinant. I mean, you can prove that it has at least you need at least linear at least.
No,
Um,
if the determinant is completely, if the determinant is the same power as the permanent, then you could.
Then you could do a projection and
no, it's not clear. Or at
It's
least
not clear at least, but potential
Yes.
is could be.
yeah, I don't know.
The
So-
theorem assume p-different characteristic of the
This
value.
simulation works only if the characteristic is different than 2.
no,
And it shouldn't work if it's 2 because.
no,
Yeah.
I guess it is clear that it will be hard to prove. Well, if you could embed a permanent inside a determinant with very, very little, less than linear, or maybe that you know. That
Yeah,
need at
you
least
know
a
that.
linear blow-up,
Yes. Quadratic.
at least quadratic.
Yes.
Yeah.
Okay, so you might be
Yeah.
able to prove that at least this
Yes.
step has to take.
Yes, you're right. Okay. So this
So
is.
we assume in the whole game that we had a field. When was field used?
So in all, so it's actually the reason we start. I'm talking about this now in some sense, is that we started thinking about what happens, for example, when the variables do not commute or are not associative. So does this whole structure collapse or not? And we know some things about it, but in these proofs, in these simulations, you assume commutativity, you assume associativity. So at least the way I will present them.
But what about Riemann 4, for instance?
It's probably works.
So this simulation, I think, will work. This will work, I think. And here, yeah, I think that here the only thing you need to have is 1 not to have an inverse. 2, like 2 to have, sorry,
Inverse for
this to be defined. I think that this is the only thing you need. Okay, so let's try to prove this. Maybe it's a,
If you want, you can talk, you can continue.
yeah, I think in this, yeah,
This space you may have.
yes, if you, I think that in this space, if we really want to explain all of them, it's good to have another meeting.
Our lectures on Tuesday seminars is online.
Yeah, so. Okay, so let's see what happens. But so let's start with the first step. So is it clear that if we prove this 3-step, then the theorem we want to prove holds? Okay, maybe one last comment before we'll take a break and then we'll do this, is that some of you were here when this raises the question of embedding the permanent into the determinant. So where this embedding is using simple substitutions. So we write xi 1, 0, x2, so on in the embedding. So if we can, so the determinant has a determinant. So this is what we discussed before as a quasi-polynomial size formula. And the permanent should not have quasi-polynomial size formulas.
What does quasi-polynomial?
So this n to the O of log n.
Polynomial maybe?
Yeah, quasi-polynomial.
So
Here is just using,
yeah, so yeah.
it's just the
Okay,
upper
wanted-
bound. It's just using the upper bound, not
This is, so this statement is that the determinant has this size formula. Yeah. Yeah. Another statement that a formula of size n to the log to the power of I of n, so for every I, we saw by the universality that was here of the determinant that this a formula of size s can be embedded in a determinant of size s. And now, if we believe, like, if a permanent, so
VNP is different.
yeah, if VNP is different than VP. In particular, the permanent does not have polynomial size formulas. Then, so we can write the permanent. So if the permanent has n to the log n formula, this in turn can be embedded in n to log n determinant. And so if VNP, yeah, and
You wanted the implication from the other
yes,
direction?
and this,
I think you want the not equal to be an equal.
Yeah, that's
Yeah,
right.
I mean, you wanted to
No,
say
no,
that
so-
if you prove that it needs at least n to the omega of log n embedding,
yeah,
then
what I
VNP
sorry.
is different from VP?
Yeah, so
Just as a question, VNP different than VP is equivalent or is sufficient to prove lower bound on embedding the permanent into
Yes.
the determinant, yes.
So like if you want to be like, just like I said, if you prove an n to the omega of log n, little omega of log n, lower bound on the embedding, then you
So okay. If the permanent can be embedded in this size determinant, then since the determinant has a formula of this size, the permanent will have a formula of this size. So the determinant has a formula of this size. And if VNP is not equal to quasi-polynomial size formulas, which we believe is the case, then the permanent should not be embedded into a determinant of quasi-polynomial size. And this question is like the first step or some step in the direction of proving that the permanent, that VNP is not equal to VP. And there are
It's also the last step, no? I mean,
so the
if you prove that, if say you prove a super quasi-polynomial low bounded, then you've proven that permanent is not in VP, right?
yes. Okay. Yes. So and the best. So this raises the question of if we have a permanent of n by n matrix, what is the minimal S that we can write permanent of X as determinant of M, or this is simple substitutions. So the question is, what is the minimal S? And the best thing that we know is that S should be something like n squared, or I think that it's really n squared, and we don't know anything better, and there are, this question has another plan that Mulmuley is presenting to show that the permanent cannot be embedded in quasi-polynomial size determinants. But we don't know this at this point. Okay. So let's have a 10-minute break, and then we'll start proving this. Okay, so we now want to simulate a circuit, a polynomial size circuit, by a Boolean sum over a polynomial size formula. Maybe I should mention that it seemed that the paper of Valiant had some leaps of faith in it, and then some people filled these gaps. So I think one of them is Joachim von Surgaten, and then also other proofs were found by Peter Burgiser and some other people. And the proof of this specific statement, I'm going to present actually a simplified proof of this statement that is quite recent. It's like in the last few years. And the two people that proved the proof I'm going to present is by two people, Malod and Portier. And in some sense, this is maybe the natural proof. So the proof of the first part will have two parts in it. So the first step is we will take a general circuit of size S and degree D.
Sorry, what is the degree?
What?
What is the degree?
The degree of the polynomial.
The degree of the
by the cell.
yeah. So yeah. So yeah. So
The true one, not the one which will be apparent.
The true one.
Those can
yeah, the output like the original.
But maybe another comment is that circuits, arithmetic circuits, can always be homogenized without
Yeah,
really
we will.
significant, because another factor of D, the degree of the actual polynomial. And then you never compute things higher than the degree.
We will actually, to prove this, we will argue this in particular. This will be one step. So we'll take a circuit of size S and degree D, and we'll transform it to a circuit of size roughly s times d to the power of 3. And this circuit will be multiplicatively disjoint. This means that whenever we have a product gate, the two circuits below it will be disjoint. So there will be no common vertex in these two graphs. This may be a bit surprising.
It's like almost getting to a formula.
Yes.
Yeah, yeah.
But yeah, it's true and it's useful as well.
Why is it not a formula?
Because so we'll have the general structure of such a circuit will have like a product gate, and then another product gate, and then so this already make it not a formula.
So I didn't understand the definition.
For every specific product gate that you choose, you look on the two circuits below, the left child and the right child. These two circuits will be disjoint.
Okay, but it's not true for the sum gates.
Yeah, and it's not even, it's not true for the sum gates, and even like,
Even if it was, it wasn't enough.
When one say disjoint, one allow variable to be common from those.
no, so for example, if you will have x1 here, you will write, like, if x1 appears both here and here,
Then you may have to make
yes,
duplicate.
you may duplicate. Yes.
Sorry?
Like we did with formulas.
Oh, we do that for formula?
Yeah,
Yeah.
for formula, otherwise you will have every variable appearing once. If you want it to 3, then you say let's duplicate formula. Variable.
So the statement is to go from arbitrary SD to multi-disjoint SDQ.
Yeah.
Yeah.
D is the same because it's the same polynomial.
Yes. Yeah.
Oh,
So.
these are-
Yeah, and this stands for multiplicatively disjoint. So.
oh,
Add the P.
Where?
LICAT.
So when we speak of scalars, we don't care about the number of variables.
No.
Yeah, in this case, we don't care. In other cases, we may care.
I mean, the number of occurrences of variables is bounded by the size. That's all you need.
So maybe before we prove this, let's see why this is useful, like a little bit, and then we'll prove. And then, so let's assume that phi is a multiplicatively disjoint circuit. Now it's even shorter. And now, in our mind, we want to prove this statement. So what is a Boolean sum over an arithmetic circuit? The only like discrete things in some sense are the edges. So this Boolean sum will be sort of on the edges of the graph. More formally, we will define a notion that is called a parse tree. A parse tree will be a subtree of the circuit. And how we will define this parse tree by induction. So the output.
Before you define the by induction, these are what generates monomials.
Yes. Yeah, I will. Yeah. Every sparse tree will compute a certain monomial, and the sum over all subtrees will be the polynomial, or parse trees, sorry. So I think it will be clear. So we always take the output gate. I'm going to define now a family of parse trees. A parse tree is a tree of the following form if always the output is in the tree. If we have a sum gate that is a sum gate and it is already in the tree, then either
Exactly one.
yes, one of V1, V2 will be in T. So when we see a sum gate, we choose either the left child or the right child and put it in the tree. And when we see the product gate, then both V1 and V2 are in T. So let's see a simple example. So this is some circuit. This circuit will have two parse trees. The first,
Another color if you want.
no, I'll put it right. So the first one, this will always be in the parse tree. Now this is a sum gate. We choose one of the child. So we choose this one. This will be in the parse tree. Now this is a product gate. Then we take both children. This is one parse tree. Another parse tree is this parse tree.
That's one.
Yes? So we, for a given circuit, we define a family of trees, which will be the parse trees.
And there are trees only because the circuit is multiplicatively disjoint.
Yes. So yeah, one statement is that one, if multiplicatively disjoint, this implies that it's indeed a tree. And the other, so maybe, and the other statement is that in this case, F is equal to the sum over all parse trees. Each parse tree computes a certain monomial. So we sum over all these monomials, and this will be our polynomial F. So F is, so this somehow translates to a Boolean sum. Trees are like Boolean variables. And this is one monomial. So it's a simple formula in some sense. And we will later show that this is indeed a Boolean sum over a small formula. Okay, so this is why multiplicatively disjoint circuits are useful for this statement. And how do we prove this statement? We prove it by induction on the gate. So okay.
It's kind of like it's just presenting f as a sum of its monomials, no?
So if it was not multiplicatively disjoint, then there might be a problem because so the product of two polynomials, we have like two independent subtrees, one for this and one for this, and we need them, the contribution of two independent copies, sort of. So.
Still the second part is going to be true. Maybe the first part won't be true.
Yeah, then you need to define a sub. So to make, So if we know that the sum over all subtrees here and sum over all subtrees here,
So the point is, if it's not multiplicatively disjoint, sort of you have and you have cycles, then you have ambiguities about which node to choose at addition gate.
yes.
So you might want to choose one on one path in one sub-expression
Mhm.
and the other
Yes.
in the other sub-expression.
Yes.
So if you just have one choice, then
You don't
you
know
won't
it.
cover all
Yeah.
the numbers.
Mhm. So, okay. So let's keep this in mind. We'll prove it maybe later. But let's see how to transform a circuit into a multiplicatively disjoint one. And the idea to use multiplicatively disjoint circuits is their idea. But we didn't put here. Okay. So before we'll do this, we'll do a simpler task, which is what Avi said. So a simple thing will be first to homogenize. A circuit. A homogeneous polynomial is a polynomial that all the monomials that occur in it have exactly the same degree. So this is homogeneous, and this is not homogeneous. And now we want to take a circuit of size S and degree D and transform it to a circuit C, which will be homogeneous. And this means that every gate is homogeneous. Okay, we want to take a general circuit. So
And you have to do it adding first one.
no, I
Not adding variables, just it will be a larger stuff.
So to do this, we of course need the output to be homogeneous. If the output is not homogeneous, we can compute each homogeneous part separately, and then only at the top combine them together. So how do we do this transformation? The size of psi will be at most the size of phi times d squared. And how we will do this transformation? Here we will have gates V. Here the names of the gates will be V and I, where I will be from 0 to D. And and we will have the property that psi of Vi is the homogeneous part of degree I of phi hat V. So we will duplicate each gate D plus 1 times. Each copy of the gate will compute the corresponding homogeneous part. And this transformation is fairly simple. So we do it by induction from input gates upwards. What to do for input gates is simple. We just, so if we have an input gate labeled by 1, then V of 0 is 1, and all the other V's are 0. So input gates for example, if V is 1, then V of 0 is 1, and V of I this is an example.
If it's a variable, then
Yeah.
it's one will be
Yeah, okay, I'll do it. If v is some xi, some v. So this is what we do for input gates. If we have a sum gate, then we can define for every I, we can define this definition, and this implies this property by induction. And the last case is when we have a product gate, and then for product gates, we define it like this. And again, by induction, the homogeneous part of degree I of V is the sum over all k's, the homogeneous parts of degree k of V1 times the homogeneous part of degree I minus k of V2. And how much did we increase, the size of the circuit? Well, we duplicated each gate roughly d times. And for every product gate, we added another d edges to compute this sum. So at most, we multiplied the size of the circuit by d squared. Okay. So to make a circuit multiplicatively disjoint will be sort of a more delicate operation of this sort. Well, we need to take care of more details, but it will have sort of a similar flavor. So So I want to say that the first step is to use our previous statement, that without loss of generality, we can assume that the polynomial we compute is homogeneous, and in fact that the circuit is homogeneous as well. This may increase the size by a factor of d squared, which will be good enough for us. And if f is not homogeneous, we compute all of its homogeneous parts separately, and then we just sum it all together, and this does not violate the multiplicatively disjoint structure. Okay, so this is the first step. So now we have a homogeneous circuit phi. Its size is S, and its degree is D. And the gates in phi are, we call them V. And now we want to transform it into a circuit psi, which will be multiplicatively disjoint. Its size will be S times D, and the degree will be D. And now the gates of the circuit psi will be labeled by V, where V is a gate of phi, and an interval I. I will be an interval of the form I plus I plus 1, I plus the degree of V minus 1 inside D. So we duplicate again each gate D many times, but we do it in a careful way. So we duplicate each gate V to be, it will correspond to some interval of length degree of V, and it will be an interval inside the set of the elements from 1 to D. And we will have two properties that we will maintain. The first property is that the polynomial V of I computes is just the polynomial V computes in phi. This is not so in terms of functionality, I will be meaningless. But in terms of being multiplicatively disjoint, I will give us what we want. And we will have the property if U and J is in the circuit V of I, V and I, if, no, so U, so let's see, V prime and I prime, so is in this circuit, then I prime will be a subset of I.
So you didn't say, but this you do for every I. The interval, you do it for each.
Yeah.
There are many intervals, right?
Yeah.
D.
There are roughly D of them or something.
D, so roughly D, but it's done for every little I.
Yes.
All the shifts of length, the degree of V.
Yes. So again, in terms of functionality, I will be meaningless, but since we will keep track of it, it will enable us to make the circuit multiplicatively disjoint. So, so there are, again, we do it by induction from the input gates upward.
This property implies multiplicative disjointness?
So it depends how we will
The products.
yeah, how we do products. So for input gates, if V is 1,
There's only the empty.
Yeah,
we
so
don't
let's-
have to have constants. We can have constants in the edges, so we don't have to worry about
yeah, so so instead of looking at the input gates, let's start the induction in the first gate that computes a linear function. All the first gates that compute a linear function. So there are gates that compute constants in the field. Let's not take a look at them at this point. So if V is some alpha times xj, it computes some linear function, then V will be V of I. So the degree of V is 1, then we have an integral from an interval from 1 to 1 So all the gates are labeled by this, and this will be, we will label it by alpha xj. And then these two properties holds, that's simple. Another simple case is that V is V1 plus V2. And now, so what do? We do exactly the same thing. So we define V of I as the sum of V1 of I and V2 of I for every I. And so the first property holds because it just holds. The second property holds because the circuit phi is homogeneous. Without loss of generality, the degree of V is equal to the degree of V1 is equal to the degree of V2. If we sum up two polynomials, two homogeneous polynomials, and they sum up to a third homogeneous polynomials, and all of them are non-zero, then their degrees must be equal. And if somewhere we compute the zero polynomial, we can ignore it. So it's not meaningful. And because this property holds, then I of V is also I of V1 is also I of V2, because all of these things are the same. And then every gate that occurs here or here will also be allowed to occur here. So this is the second property. And the third property, now maybe this is like where the multiplicatively disjoint part should occur. Sorry, I wrote plus, yes.
So you just glue contiguous intervals in all possible ways.
So there's only one possible way.
No, for all, yeah. There's one possible way for it.
Yes. So because it is a product gate, the degree of V is the degree of V1 plus the degree of V2. Then every interval of length degree of V we can break into two consecutive intervals. One of length degree of V1. Sorry. One of length degree of V1, and the other is the complement, the interval that comes after this interval up to I plus the degree of V minus 1. So in terms of functionality, again, this is just, we can ignore I and everything holds. Now, this interval and this interval are contained in this interval. So this means that the second property holds. And now this circuit is multiplicatively disjoint because of the second property. Every gate that occurs here does not occur here because these two intervals are disjoint. So
And the interval is part of the name.
yes, yes. Okay, so we somehow kept track of where we in some intuitive way, I tells us in which, so yeah, I'm not sure if it will be more
Maybe
confusing.
for every variable, you introduce d copies of it.
Yes.
And you keep track. This I helps you keep track which copy of the, it's like one copy for every position in the monomial.
Yes. Yeah.
And this helps you keep track of which occurrences of variables contribute to the monomial in the tree structure.
Yes. So, yeah. So if all of this were done in a non-commutative world, then every variable will have a certain position in a monomial, and this I will tell us where do we look, like where do we use this variable. Okay, so this is proving that circuits are multiplicatively disjoint. And now we want to use this to simulate a circuit by a formula.
These arguments indeed work as well or even better in the non-commutative.
Yeah, it may be even more like easier to think about it. Yes. Okay, so so now we concluded that circuits without loss of generality are multiplicatively disjoint. So when we want to simulate a circuit, we can assume that this circuit is multiplicatively disjoint. And now we will use the fact that for multiplicatively disjoint circuits can be written as the sum of their parse trees. So maybe I will postpone the proof of this equality if we'll have time at the end of the talk. You'll prove it by induction on the circuit. And
Just the intuition that Avi said, it's just the sum of the monomials, right? This is
yes, there is this issue that you need multiplicatively disjoint to have.
to get the right counting,
Mhm.
to make sure that the
Yes.
coefficient is the right one.
Yes. But let's see how to use this. So the intuition, again, we want to write it as a sum over E, G of E and X. This is what we want.
F is f of x and t is t of x.
Yes.
Intuitively, the e's could say whether a node is in the parse tree or not.
Yeah.
So, the E will have, okay, yeah, the E will indicate, the E will run over all possible subgraphs of phi. First, we will check in polynomial time whether this subgraph is a parse tree. Then, because this can be done in a Boolean circuit of polynomial size, we will show that it can be simulated by a small formula, or we will explain at least. And so I want to say that this will actually be of the form sum over, so I want to sum and we'll do it layer by layer. E will represent a subgraph of the formula of the circuit phi. Then using a small Boolean formula, we can check whether E is actually a parse tree in polynomial time. Because if you have a circuit and you are given as input some of its edges, it's pretty easy to check if these edges form a parse tree or not. And then after we concluded that if a certain E is a parse tree, then what is the monomial that this parse tree computes? So if we have a Boolean variable for every input gate that indicates if it is in the parse tree or not, then when we multiply all of these, we get, so if E is parse tree, T, then this thing will be the polynomial that, the monomial that T computes. It is the product of all input gates in this tree. And so here, this will be either a variable or a field element. If this is 1, then this will be 0, and we'll just choose this part. And if we didn't choose E of E, this will be 0, then all of this will be 1, and we can ignore it. So I'll try to make it more formal. So for every V and U in psi, in phi, this will be Boolean. So we will define a Boolean vector of size s squared. The length of this Boolean vector will be roughly s squared. And we'll have entries of the form VU for 2 gates, V and U in the circuit. And we will have variables of the form E of V, where V is a gate in the circuit. So the length of E is at most S just 2.
What do you need the edge variables?
Check that it's a
this
parse
to
tree.
No, but even
No,
In the first one, in the first Boolean formula, checking that it's a parse tree.
that seems like you could just write down your definition of parse tree. And
So-
that each of those is
Yeah, I mean, that's
So-
you need edge variables.
you need to encode a parse tree by a Boolean vector.
yeah. But
So-
what if you just have the gate variables? Then you just need to say for every multiplication gate, both
Yes,
children,
mhm.
if it's 1,
Yes.
then both children are 1. And for every addition gate, if it's 1, the parity of its children is 1.
Mm-hmm. Yes. I think maybe
I'm confused. V and U are what are vertex of this?
yes, yes. This,
That's adjacent or not adjacent?
no, just every 2 gates. So yeah, we can do also what Russell said, but I think this, at least to me, it's a bit simpler to think about it. So this EVU encodes subgraph so even more than, like, okay, so
I don't see how even you could
Yeah.
have seen
Yeah, so this is right, I changed it.
Maybe disconnect.
It, it,
No, it's edge or vertex.
so now, yeah, I did, so it's not, so here I wrote edges. V and U are edges. So every choice of values to 0 or 1 to the edges, either we keep an edge or we,
So
Maybe you don't want to do it. I mean, I think it's a programming. It
But,
just, say what you want.
I think
Yeah.
it's not,
It's not obvious.
yeah, not hard.
what Russell said doesn't work?
Yeah, so I think this is easier to see, but I don't, yeah, you can do it in many ways. It's,
So
yeah,
for each edge you have a Boolean variable.
yeah, for every edge you have a Boolean variable, and this Boolean vector encodes some subgraph of the original circuit. So what will this Boolean formula do? It will first check if E is parse tree. So this task has a polynomial size Boolean circuit. So there exists a Boolean circuit B, the size of B. So since we can check if E is a parse tree in polynomial time, this means that there exists a Boolean circuit that given input E is 1 if and only if E is a parse tree. And now we want to transform this B into an arithmetic formula. So how do we do this? The first step is to transform B into a Boolean formula of roughly the same size. So this is Boolean. And we do this, so what does this mean? That for every E prime, so we take the circuit B and write it as a Boolean formula in a bit more variables, E prime, and this formula will evaluate 1 only if E is a parse tree. E will be some part of the input, and this is something that is, it's like in the,
That's exactly Cook.
yeah, it's, this is like a well-known theorem that you can do this. And the idea is pretty simple. The new variables E will check consistency in the circuit. So it will, so I'm not sure I can explain it in 5 minutes in a good way. Can any of you?
No, everybody should.
The new variable, so it doesn't depend on the value of the new variable.
So okay, I'll try to. So there is the circuit B, and it has inputs E. We'll write it into a formula, and the variables here will be either E or
This particular circuit that you're looking, wasn't it the formula in the first place? Or?
So
Is it just an end of many small conditions?
you can, yeah, I didn't want to write it explicitly. It's true in general, in so generality that. So the other input to this formula will be some new variables e prime, and e prime will be variables that are assigned to edges in this circuit. Now, given an input e, these variables, each variable, we will check in this formula if the local conditions here hold. So, for example, if we have an edge E1, E2, and here we have some value and value, we check that, like the so.
Catch it really is the end.
Yeah, you check. Yeah, okay, I'll do that.
The statement is just for example, whether a circuit computes a certain value can be translated, a circuit can be translated into a formula, which about which you ask the same question: does it compute a certain value on a given input? The way to transform a circuit to a formula is just by adding more variables to tell you exactly what value is carried by every wire of the circuit, and then the formula just checks that every gate computes what it should. So it just becomes a big conjunction of local conditions. It becomes a formula.
But what's the relief with B of E and F of E prime? I want some equality.
Yes.
The,
So
the
there is
sum,
a
the
question.
sum
The
over
sum
all
of
E is equal to the of B of E is equal to the sum
Yeah.
over all
E prime.
Ah.
Yeah.
Oh.
Yeah, so
The sum of the
maybe I
prime.
should.
Oh,
So
If there's anything to use a general Boolean circuit of polynomial size can be turned into a
Formula. If you
No.
care just about the sum of the, if you just want to know the sum of the values of the circuit on all possible Boolean assignments, then
Yeah, you
it would be the
oh
You
the
can
same
write-
as the sum
Yeah,
of
that's
the
useful.
similar, yeah, so it's obvious.
You can write of B of E as the sum over all E double prime F of E comma E double prime. Yes, that's the equality.
and this added variable also take value 0 or
Yes.
1.
yes. And the final step, it's is to transform this formula into an arithmetic formula, and this is also pretty straightforward. So, so we can assume that this formula is actually like a Friesian. It's like a
So you don't have to assume anything. You just say simulate and by multiplication of Boolean variables
so you want.
Or
and
All
negate,
by sums.
not by some,
By
you know,
yeah,
use
making
more,
sure that it's always the answer.
negation is
negation.
1 minus,
Ah, okay.
and then you have negation and you can do or.
Yes.
Yeah, okay. So, yeah, so the last step is to simulate a Boolean computation just over the Boolean, a Boolean computation into an arithmetic computation that will work only over the Boolean cube. But since our inputs are always in the Boolean cube, we can write here some arithmetic formula that checks all of what we want. So we started with a sum over parse trees, and we got into a sum over an arithmetic formula that checks some Boolean things times a product of things. And all of this is a small small arithmetic formula. And this is exactly what we wanted. And this proof shows that where the intuition we started about VNP, that a polynomial is in VNP if we can find its coefficient efficiently, then the same kind of proof shows this as well. So this will be an arithmetic formula that will check, that will get as inputs an encoding of the monomial in binary, and will check, will compute its coefficient, and then we just multiply it by the monomial.
But it's not exactly true because the same monomial, I mean, it's the other direction, right? If you can compute.
Yeah, if you can.
Just one direction. If you can compute the coefficient, then you can write it down in this way.
I thought that this will be.
No, because you can have the
nice.
same monomial appear for two different parse trees can yield the same monomial.
But here, if we want just the VNP statement, there are no parse trees. The encoding will be of the coefficient of the monomial in binary.
He's talking about the different direction. He's talking about whether the reverse direction.
You're talking about, okay. So,
And that's
I'm
not
sorry.
obvious because
Yes.
with this representation, maybe the same, you have contributions to the same monomials, to the same monomial from several
Yes.
parts.
yes, okay, yes. So yeah, I think we'll continue somewhere.
So if we wanted, I mean, to just shortcut, I guess, if you wanted step 2 and not in full generality, then this formula has a particular form, right? It's a product of many constant size things.
There is this Boolean part
That's
exists
also
alone.
CNF, right? It's like a.
Yes, you can make it into a
So
CNF, yes.
that will be like not too hard to embed as a determinant of a block matrix,
Yes.
like with
Mhm.
constant size
Yes.
blocks.
Yes.